Let's talk a little about simple linear regression and specifically the least squares regression line. If you recall our assumed relationship between y and x in simple linear regression, that y is equal to beta naught plus beta 1 x plus epsilon. Now, beta naught and beta 1 are the parameters of our model here, but we do not know what their values are, as is usual for parameters in statistics, and so we want to estimate them. And so we use sample data to find our estimated regression line. And our beta naught hat is our estimator of beta naught, and our beta 1 hat is our estimator of beta 1. Now the question is, how are we going to come up with good estimators there? What are we going to use for beta naught hat and beta 1 hat? How are we going to get them? What rule are we going to use to get them? And what are their formulas in the end? First, we need to talk a little about residuals. A residual is the observed value that we see in our sample data minus the predicted value from the model. And the notation we're going to use here is that the ith residual, E sub I, the residual for the ith individual, is equal to the observed value of y for that ith individual minus the predicted value of y for that ith individual. Now, each individual is going to have a residual associated with it. Let's see what this looks like in a plot. Here we have a scatter plot, and we have our estimated regression line drawn through those points. And the residuals, as you see here, the residuals are these assigned vertical distances. So the distance between the point and the line for all of these points. Every point has a residual associated with it, the vertical distance between that point and the line. Points below the line have negative residuals, and points above the line have positive residuals. Now, how are we going to choose our line? We want a line that fits through those points well. So one thing we might think of is, how about minimizing the absolute value of the residuals? Or in other words, minimizing the total vertical distance of those points to the line. Now, that sounds pretty reasonable. That's this rule that I've laid out here, minimizing the total vertical distance from the points to the line. Sounds reasonable, sounds like something a logical person might think of, but it is not the rule that we use. We use it sometimes in the world of statistics, but we don't typically use it. We typically use something a little bit different. So we're going to leave this aside and move on to the method of least squares. In the method of least squares, beta naught hat and beta 1 hat are chosen to minimize the sum of the squared residuals. Here is our observed value of y. Here is our predicted value of y. We're taking the difference, squaring it, doing that for every value and adding them up. And our beta naught hat and our beta 1 hat are the values that make that as small as possible. How are we going to do this? Well, we're going to use a little calculus, and we're going to write it out in this fashion. And our y hat is equal to this. And so when I want to minimize that quantity, I use a little calculus, and I say, hey, wait, what I can do is take the partial derivative with respect to the slope, take the partial derivative with respect to the intercept, set them equal to 0, and solve. Now, that's how we'd actually derive the formulas for those quantities, but we're going to avoid that. I'm going to skip to the actual answer here, what actually happens, the formulas for those. But first, we do need to know a little notation. Our SSXX is also known as our sum of squares for x. Our SSYY, our sum of squares for y, and our, what I'm calling SSXY, which is our sum of products between x and y. Now that helps us with the notation here and writing it out a little bit cleanly, because here are our formulas. Our beta naught hat is equal to y bar minus beta 1 hat times x bar. Now that's not much good without a formula for beta 1 hat. Luckily we have one just below. Our beta 1 hat is equal to our sum of products over the sum of squares for x. And those are our least squares estimators. And we use the least squares method because these estimators work very, very well in a variety of spots. In some situations, they are the best estimators that we could possibly use. Very commonly used, this least squares approach. So let's take a look at our example here. Pain-related brain activity versus score on the empathic concern scale. I want to fit a line through these points. So I'm going to say that my line of best fit is going to look something a little like this. And, well, let's see what the least squares method tells us. We're going to use a computer to come up with these values. A computer is going to give us our values here. And this is our output from the computer package R. Different computer packages look similar, but maybe a little different. And this is going to give us our line, our intercept line, and our slope line, and our regression line is this, minus 0.37452 plus 0.03454 times x. This is our beta naught hat, and this is our beta 1 hat, and we get those straight from our output. There's our scatter plot with the least squares regression line superimposed. Now, this line has minimized the sum of these squared vertical distances, the sum of the squared vertical distances between the points in the line. You cannot possibly have a line with a sum of squared vertical distances that is smaller. Couple of points to finish. For least squares regression, the residuals always sum to 0, and the line always passes through the point, mean of x and mean of y.